So homework day 40, the end of the pie chart. These are the last few things on your pie chart, and you should be able to finish your pie chart. Starts with the Pythagorean Theorem. So, many years ago, before TVs, computers, and all the fun things we have, there was a guy named Pythagoras. He figured out that if you have a right triangle, that the sum of the legs squared is equal to the hypotenuse squared. Well, what in the heck does all of that mean? The legs of the right triangle are your two short sides. I'm going to label them A and B. The hypotenuse is the side that is opposite the right angle. That's your long side. Right? That would always have to be longer than the other two sides if it's opposite that right angle. So Pythagoras came up with the Pythagorean theorem that says if you do a squared plus b squared, it's equal to c squared. The sum of the legs, the two short sides squared, is equal to the hypotenuse squared, the longest side squared. So on this problem, you want to make sure you pick out which one is the hypotenuse, because that's the one that's going to be by itself after the equal side. So here would be my two legs. Here's my hypotenuse. 9 squared plus 11 squared is going to equal x squared. I've got it all set up. Now again, Alex probably solves this in a little bit different order than I do, but I like to get rid of my squaring first. So 9 squared, 9 times 9, 81. 11 squared, 11 times 11, 121. 11 squared plus 100, or 9 squared plus 11 squared, 81 plus 121 is equal to x squared. So I'm going to add those. 81 plus 121 is equal to 202. Well, that's equal to x squared, not just a plain x. So, when I solve this, it was a really long time ago that we had some with x squareds in, but when I solve it, I have to do the opposite of squaring. So to get rid of that squaring, what I'm going to do is do the square root of both sides. The square root of an x squared is just a plain x. On this one, I'm going to use my calculator because I'm going to round to the nearest hundredth. So I'm going to grab my calculator. The square root button is right next to the fraction button. I'm going to do the square root of 202, and I'm going to hit equals. I get 14.2126, so forth and so on. I want to round to the nearest hundredth. 2 places after my decimal, since there's a 2 behind it, I'm just going to leave that as 14.21. Now my hypotenuse should be the longest side. It is longer than the 9 and the 11, so that looks like a good answer. 14.21. Number 2, we are still doing the Pythagorean theorem because we have a right triangle. Again, when you're thinking about the Pythagorean theorem, you're saying a squared plus b squared equals c squared, and that's always the long side, the hypotenuse. Well, which one is my hypotenuse? In this case, the 11 is my longest side. So when I set up my Pythagorean theorem, I'm going to say 10 squared plus x squared equals 11 squared. The 10 and the x, if you switch them around, it's fine. You're going to get the same thing because they're on the same side. But the 11 has to be on that other side. So 10 squared is 100 plus x squared equals 11 squared, 121. Now in this one, to solve it for x, I've got to move my 100 over with my other number because I've got to get the x by itself. So I'm going to minus 100. X squared is going to equal 21. I then have to solve that by getting rid of the squared, so I take the square root of both sides. The square root of x squared is just x. I'm going to do the square root of 21 on my calculator, 4.582, and so rounding that off to the nearest hundredth, x is going to be 4.58. Right, that should be shorter than my hypotenuse. So that looks like a good answer. The third one, using my Pythagorean theorem. Now they got my triangle turned all topsy-turvy, but if I look, here's my right angle, so my hypotenuse is the 13. setting up my Pythagorean theorem then, x squared plus 10 squared equals 13 squared. So getting rid of my squaring, x squared plus 10 squared, 100, equals 13 squared. 13 squared, 169. Again, on this one, I want to get the x squared by itself, so I've got to move my 100 to the other side. X squared equals 69. And now I want to get the x by itself, get that squaring out of there. The opposite of squaring, taking the square root. So on my calculator, the square root of 69 gives me 8.3066. I want to round to the nearest hundredth. Since there's a 6 behind there, I got to round that up to 8.31 then. And again, that's one of my legs, so it should be shorter than my hypotenuse. It is. So it looks like a good answer. So key to the Pythagorean theorem is that the hypotenuse, the long side, is the one always over here by itself. The sum of the legs squared is equal to the hypotenuse squared. The next ones, we are doing the square root of a perfect square monomial. Monomials just tell me it's going to have variables in there, and we haven't done the square root of variables yet. But thinking about square roots, I'm going to start with the square root of 4. The square root of 4 means what times what gave me 4. Well, we already knew the square root of 4. It was a 2. If I take 2 times 2, I get 4. If I'm going to do the square root of y to the 8th, you're thinking about what times itself gives me y to the 8th. Well, when we are multiplying with variables, we add the exponents. 4 plus 4 gives me 8. The key here is understanding that the index to a square root is 2. I end up taking half of my exponents. Half of 4, or half of 8, gives me 4. So the square root of 4y to the 8th is 2y to the 4th, because if I took 2y to the 4th times the second 2y to the 4th, I'm going to get 4y to the 8th. No square root left on that because it is a perfect square. So anytime I have an even exponent, it is going to be a perfect square. So all of these ones you start with here are going to have even exponents. So if I'm going to do the square root of 16x to the 12th, the square root of 16 is going to be 4. 4 times 4 is 16. The square root of x to the 12th, you do half of that, x to the 6th. If you take a 4x to the 6th times the second 4x to the 6th, you get 16x to the 12th power. So 4x to the 6th is just going to be your answer. Number 6, same kind of thing. What's the square root of 36w to the 4th? The square root of 36 is 6. The square root of w to the 4th. Half of 4 is 2, so w squared. 6w squared times 6w squared would give you 36w to the 4th power. So always half of my exponent when I'm doing the square root of a variable. The next ones, doing cubed roots. The cubed root is opposite of cubing. So I'm trying to figure out what number to the 3rd power would give me negative 8. Well, if I'm thinking about it, I want to start 1 times 1 times 1. Well, that's just 1. 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. Hey, the cubed root of 8 would be 2. I want to do the cubed root of a negative 8. So, hey, cubed root of negative 8 is going to be negative 2. Because if you took negative 2 times negative 2 times negative 2, guess what? You get negative 8. So, it says find the value of the cubed root of 64. Well, we knew 1 times 1 times 1 was 1. 2 times 2 times 2 is 8. 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. Not big enough. 4 times 4 times 4. 4 times 4 is 16. 16 times 4. Hey, there's my 64. So the cubed root of 64 is going to be 4. Because 4 times 4 times 4 is 64. Number 9, find the cubed root of negative 27. Well, we already looked up here and said 3 times 3 times 3 is 27. So the cubed root of negative 27 is going to be negative 3. Now if I wanted to check these with my calculator, I do have a cubed root button. The cubed root button is in yellow right above the x to the third power. So I would hit shift and the button that has x cubed on it. That's going to give me this on my calculator. Shift x cubed. Gives me that little symbol. I'm then going to type the number underneath. In this case, negative 27. And hit equals. Notice on my calculator, gives me the negative 3, because negative 3 times negative 3 times negative 3 is negative 27. So that's how we get the cubed root, shift x cubed, and then we can check it on our calculator. But try to do it first. Knowing your cubes, you might just want to list the perfect cubes on your paper. 5 times 5 times 5. 5 times 5 is 25. 25 times 5 would be 125. So 1, 8, 27, 64, 125. Those are your first 5 perfect cubes. The next ones, we are simplifying the square root of a whole number less than 100. Now these are going to be ones that are not perfect squares. If you took your calculator and put in the square root of 45, you get one of those irrational numbers, 6.7082033932. Irrational numbers, non-terminating, non-repeating decimals. Well, they tell us to write it in simplified radical form. We can simplify it by factoring it into a perfect square times its other factors. So when I'm working with square roots, I want to know what my perfect squares are. 1 squared is 1. 1 times 1 is 1. 2 squared, 4. 3 squared, 9. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. 10 squared, 100. Obviously, I could keep my list going. My board moved on me again, but we can move that back. So, whenever I'm working with simplifying square roots, I want to keep in mind what my perfect squares are. I'm then going to look at the 45, and I'm going to divide that up into two factors. What times what is 45? One of my factors, I want to be the biggest perfect square that divides evenly into 45. So 100's too big, 81's too big, 64's too big, 49's too big. 36 doesn't divide into 45. 25 doesn't divide evenly into 45. 16 doesn't, but 9 does. I can make this 9 times 5. Now if I wanted to, I could write it as the square root of 9 times the square root of 5 and make 2 separate square roots. I'm just going to leave 1. Then what I'm going to do is I'm going to take the square root of the one that's a perfect square. The square root of 9 is 3. So I write it as 3 times the square root of 5. Of course, I don't need the times sign in between. I can't even talk today. So if I were to check this, if I took my calculator and did the square root of 45, I get 6.708, so forth and so on. If I take my calculator and do 3 square root of 5, I should get the exact same number. 6.7082, so forth and so on. So you can kind of double check yourself by putting them both in your calculator and seeing if you get the same decimal number. Number 11. I want to rewrite the square root of 48 in simplified radical form. So I have my square root. I want to factor 48. I want to be sure I use the biggest perfect square that works. Obviously, all of these numbers are too big. 36 doesn't divide into 48. 25 doesn't divide into 48. But wait a minute, let me check 16 out. 48 divided by 16. 3 times. So I'm going to say this is 16 times 3. I'm then going to do the square root of the 16. The square root of 16 is the nice whole number 4 that goes out in front. The 3 is going to stay under my square root. So I get 4 square root of 3. Now the problem with simplifying the square root of 48 is a lot of people will say, oh, 48, 4 goes into 48 because they know 4 is a perfect square. If I take 48 and divide it by 4, it goes in there 12 times. And then they say, okay, the square root of 4 is 2 times the square root of 12. If you put in that answer, it's going to say you can simplify it further because 12 can be factored again. 12 is 4 times 3. The square root of 4 is 2. I have to multiply that by what's that in front because that's multiplying. 2 times 2 is 4. And notice I got the exact same answer, 4 square root of 3. But this took me a lot more work because I didn't pick out the biggest perfect square that goes into 48. So you want to be careful on things that are divisible by 4, that possibly they're also divisible by 16, and I can use a bigger perfect square. So always try to use the biggest one. I start with my list and just work my way backwards till I find the first perfect square that divides into my number, in this case 48. Number 27 then. I want to factor 27. The biggest perfect square that happens to go into 27. 36 is too big. 25 doesn't work. 16 doesn't work. Oh, but 9. 9 times 3 happens to be 27. The square root of 9 is the nice whole number 3 that goes out in front. I have the square root of 3 left over underneath. And so 3 times the square root of 3 is my answer. Those might take you some work. Like I said, always keep that list of perfect squares handy. It makes your life a little easier to just check your numbers and work your way backwards. 13, 14, and 15, we are solving a radical equation. Going to have square roots in these ones. If I have a square root in the problem, I want the square root term to be by itself. It is on this problem. And to get rid of the square root, I do the opposite, which is squaring. So I'm going to square both sides of my equation. Now if I think about this with a number, if I have the square root of 3 squared, that means I have the square root of 3 times the second square root of 3. Square root of 3 times the square root of 3 is 9. Well, 9 is a perfect square. I can do the square root of 9. I just get the plain whole number 3. So, squaring undoes a square root symbol and you get whatever's underneath. So, squaring the square root of w minus 11 would just give me w minus 11 and it gets rid of the square root symbol. The other side didn't have a square root symbol. 5 squared, 25. I then solve this like I solve everything else, so I'm going to add my 11, move it to the other side. W is going to equal 36. Now when you're working with square roots, sometimes you get what's called extraneous solutions. Although you did all the work correctly, the answer doesn't check. So you always want to go back and check your answer. Is the square root of 36 minus 11 equal to 5, right? I put the 36 in for the W to check it out. Well, 36 minus 11 is 25, and sure enough, the square root of 25 is 5. My answer does check, so that's a good solution. Number 14, I'm solving for u. Again, this one has a radical symbol in it. It has a square root, but it's not by itself. So before you can square both sides, you have to move the number to the other side and get the radical by itself. So in this case, I'm going to go ahead and add my 2 and say the square root of u minus 6 is equal to 5 plus 2, which is 7. Now that I have my radical by itself, now I can go ahead and square both sides and use my rule. If I square my square root, I just get the u minus 6. 7 squared is 49. I want to go ahead and solve that, so I'm going to just go ahead and add my 6, and u is going to equal 55. Again, I want to check my answer. 55 minus 6, square root of 55 minus 6, minus 2, does that equal 5? Well, 55 minus 6 gives me the square root of 49. The square root of 49 is 7. 7 minus 2 is 5. Yep, that checks out. So that is a good answer. Number 15. I want to solve this for u. Again, the square root is not by itself. I need to move the 14 to the other side. So I'm going to minus my 14 and say the square root of u plus 20 equals negative 13. Some of you might think there's a problem to begin with right here. Some of you might not recognize the problem. So we're just going to go ahead and solve it. To get rid of my square root, I square both sides. Squaring my square root would give me u plus 20. Negative 13 squared. Make sure you use the parentheses. I have to remind you of that all the time. Negative 13 times negative 13 is a positive 169. Solving that, I would minus my 20, and I would get u equals 149. I'm going to go ahead and check that. 14 plus the square root of 149 plus 20, does that equal 1? That was my original problem. 14 plus the square root of 149 plus 20 is 169. The square root of 169 is 13. Well, 14 plus 13 is 27. Wait a minute. 27 doesn't equal 1. Even though I solved that correctly, that answer is not going to work out because when I squared this negative, became a positive, and I got one of those extraneous solutions. Square roots are never going to equal negative numbers over here. That's why I said some of you might have recognized right away that, oh, I can't do that. But had I finished the problem and went back and checked it, I'd for sure find out, nope, I can't do that. Square roots can't equal negatives. And so in this case, my answer, no solution. And you will have some that come up to no solution. So make sure you check your answers when you're done to make sure they come up correctly. Last three things on your pie chart are converting between radical form and exponential form. So, radical form. If I have my index, I'm going to say m to the x to the nth power. That would be radical form. In exponential form, I'm going to write my exponent as a fraction. The index to the radical is the denominator of your fraction. So this would be n over m. Notice where those went. This one on top, this one on bottom. So they're going to have you practice converting from one form to the other. If I'm in radical form, they're going to have me put it in exponential form. This would be t to what power? The 4 goes on top and the 5 goes on the bottom, so t to the 4/5 power. If you take intermediate algebra and college algebra, we'll put numbers in there and actually have to solve them. But for right now, we just want to practice the switching around. X to the 1/3 power. So, the 1 goes with my x. The 3 is the index to my radical. Now, of course, we know that we don't really need x to the 1st power. So we're just going to say it's the cube root of x, and that would be your answer in the best form. Number 18, write it in exponential form again. Now in this case, there's not a number written in there. We know that if there's not a number written in there, that's a square root, and that the index is understood to be a 2. So this would be n to the 5/2 power, right? If my denominator is 2, it's a square root, and on square roots we don't need the 2 written in there because we understand it's a 2 instead of having to write it in there. All right, so they will have you do some practice here and then try to get your answer in the best form. If it's to the first power, we don't really need the 1. If it's a square root, we don't need the 2 written inside on a radical. And that is all of the topics that you have on your pie chart, so you should be able to finish those up and be ready to take the final.